morning, everyone. Thank you for being here today. And I want to thank Google for inviting me to give this talk. Today, I'm going to be talking about iceberg distribution around the Greenland Ice Sheet. And this is part of my research at the University of Kansas. And I'm going to be sharing how I use Google Earth Engine and Google Colab for my research here. So before we begin, we want to know why icebergs are important. So icebergs are an important part of the climate system since they interact with the ocean, the atmosphere, and the cryosphere. As we know, the icebergs calve from the glaciers and the ice shelves, and they carry substantial amount of fresh water once they calve off. This calving event leads to impact on sea ice formation, on fjord circulation, as well as local and nutrient fluxes that are carried and that are carried with it. So a continuous multi-year iceberg distribution database can provide very important information about seasonal changes in calving as well as fjord circulation. CGCM models or the coupled global circulation models rely heavily on iceberg distribution parameters since they are used to estimate the freshwater budget. The recent decline that has been observed with the sea ice extent has increased, and we have seen an increased shipping and mining activities as well as hydrocarbon exploration. And these require real-time iceberg distribution for logistics and safety purposes. In this image, you can see this is the 2021 snapshot of the shipping activity around Greenland. So you can see here the southern and the western coast of Greenland has a high density of shipping routes. And as I said earlier, the iceberg distribution information becomes more and more critical for such reasons. So there are several challenges when we are looking at the entire ice sheet wide iceberg distribution. So first, like I said, is the automatic detection of iceberg in a range of environments is quite challenging. So we come across things such as sea ice, melange, mixed water conditions, rough ocean waters, and brash ice. I'll show the examples of these in a few later on the slides, and that makes it quite challenging to interpret what the icebergs are. SAR images, I'm using a remote sensing platform, Sentinel-1 SAR imagery for my study, and SAR images are inherently quite noisy. And on top of that, we have complex environmental conditions that makes iceberg detection much more challenging. So, for example, when we're looking at icebergs in a melange is a mix of sea ice, brash, icebergs, and granular bits that is extremely bright in the backscatter signature. So, when you're looking at icebergs within the melange, the icebergs appear darker compared to the melange backscatter values. However, when you look at icebergs in open water conditions, icebergs appear bright. So as you can see, the backscatter signature fluctuates throughout. And so these signatures also change significantly when we are looking at sea ice and rough water conditions, because then the icebergs backscatter values as well as the sea ice and rough water backscatter signatures can overlap. So on top of this, we have the ice sheet wide detection, which is an extremely large area that we are looking at. So this makes it very challenging. There has been some previous works that have been done on the icebergs, on iceberg detection, but they have been limited either because of optical remote sensing platforms and also based on limited number of fjords that these studies were done on. And so in this, to overcome this challenge, we use Google Earth Engine. So as you can see in this research, I'm covering 260 fjords around Greenland. That is equivalent of 109,000 square kilometers of area. And this detection of iceberg is being done every 15 days for a 5-year period. So from 2017 to end of 2021, we are covering icebergs every 15 days in all fjords of Greenland. So Google Earth Engine came in very handy for this purposes because number one, there is no pre-processing needed for Sentinel-1 SAR imagery. So Sentinel-1 SAR imagery inherently requires a pre-processing before you can start using that imagery. However, that pre-processing takes time, especially if you're looking at 5 years of data. That's 6 months of pre-processing that you need before you can actually start working on the data. So that took away a lot of legwork from my end because the images are already pre-processed. Second of all is the visualization aspect. So when you're looking at a mosaic that will be covering the entire Greenland ice sheet, that's a very large mosaic to load in ArcGIS or QGIS. You cannot do that. It takes a lot of time. And if you're doing a lot of testing, going back and forth between the model that you're working on, you need rapid visualization. And that's where Earth Engine came in really handy. So like I said, we are covering a really large area, 109,000 square kilometers. We are covering every 15 days for 5 years. So for that purposes, we are using Sentinel-1 SAR imagery. So Sentinel-1 SAR imagery doesn't get affected by cloud cover because of the wavelength that it works on. And second of all, it is an active it's an active system. So basically, it has its own light source. So it doesn't depend on solar radiation. So you can, during the winter months in the northern latitudes, you are not impacted by lack of solar radiation. And because of the dynamic environmental conditions that exist, we wanted to add robustness in our methodology. And for that reason, we are using machine learning to determine what the icebergs look like. So the Sentinel-1 SAR imagery primarily that we are using comes in the IW swath because that's the highest spatial resolution available. And for this purposes, we are using the spatial resolution that it comes is 20 by 22 meters. And since it's a level 1 product, it has been resampled already to 10-meter pixel space. So here are some of the environmental conditions that we come across on a daily basis when we are looking at icebergs around the Greenland ice sheet. On the left, you can see a melange. So this is in southeast Greenland. On the top left, you can see that's the terminus of the glacier, of Helheim Glacier. And you can see the icebergs here as darker bodies within this bright backscatter. So this is how the icebergs look within the melange. On the right-hand side, as we move south on the fjord, you can see there's sea ice and water highlighted here, and the icebergs within them look quite different. They are much brighter compared to the backscatter values that we see with the sea ice, water, as well as crash ice. So this tells you the complexity, and these environmental conditions actually fluctuate within a single scene. So it's not like you're looking from one season to another. Within the same scene, moving like say 10 to 15 kilometers, this changes are seen. So this is a very rapid and dynamic environmental condition that we come across in most of the fjords in Greenland. So to prepare this data, one thing that is needed is incidence angle correction, because that's something that the Sentinel-1 SAR imagery needs. The image normalization was done so that the convergence of the data points can be done for the machine learning model. And thirdly, I use GLCM textures, which is the gray level co-occurrence matrices. So the GLCM textures provide a lot of information that in general we don't have. So for example, when we're looking at optical imagery, you have say 10 or 12 bands that you're working with. In Sentinel-1, you're looking at only at HH or HV polarization. So when you have that, then you want to create more information for the machine learning model to learn more information about the background as well as the icebergs that are seen in the imagery. So for that reasons, we are looking at I created the GLCM textures, and these textures provide information such as entropy, correlation, mean, contrast, dissimilarity, to name a few, so that we can identify the icebergs much more convincingly in images. So because of the large size of the images the region that we are looking at, if you want to export the entire mosaic out, then we are looking at roughly 500 gigabytes of storage size per mosaic. So we are looking at roughly 500 gigabytes of size per mosaic. So in total, I have 111 mosaics. So that's roughly 55 terabytes of data that we are looking at. And so in order to successfully export it out of the Earth engine onto the Google Drive, I divided the Greenland Ice Sheet into 20 grid cells. And that reduced the overall startup cost on the Google Earth Engine servers. And to export a single mosaic or a single epoch, it takes roughly 12 minutes to activate it on the Google Earth Engine servers. So for this study, I'm using random forest supervised classification model. The reason for it is because it's based on multiple decision trees, and that's why it makes it a quite stable prediction system that we are working with. And it's on top of that, it's extremely fast, and it's within because it's within the Google Earth Engine ecosystem. To determine what features I'm going to use, I use the GLCM textures along with the HH and the HV polarization bands. I implemented some edge filters that helped in determining how the iceberg edges are looking, because the edges usually have a really bright backscatter signature, and that can help delineate icebergs from its surroundings. So on top, you can see this is a Sentinel-1 SAR imagery that we are looking at, and in the bottom is the predictions that is done using the random forest model. These predictions are outputted as a probability map because of the complex conditions. If you go by default classification, you're looking at the probability value classifies at everything at 50%. But if you want to have a more control over it, you can also have an option within Earth Engine to export it as a probability map. And when you do that, you can customize what probability works best for you when it comes to final classification. So here is an example that shows the 20 probability maps that were exported out. So in total, I have 111 mosaics that cover the time period from 2017 to 2021. And that equals to 2,220 grid cells that needed to be exported out from Earth Engine to the Google Drive. Once the export task is done, I created something called the dynamic thresholding that works on top of the random forest machine learning model. And this workflow was done within Google Colab. So dynamic thresholding is needed for regions such as when we are looking at transition from icebergs within the melange to icebergs in open waters, as you can see as we move south of the fjord. So what ends up happening is it provides two constraints on how the detection needs to be done. The first constraint is the size of the iceberg. So through a lot of empirical analysis, we came to the conclusion that the maximum size of icebergs that are seen around Greenland is somewhere around 2 square kilometers in area. And the minimum size is 1,000 square meters that we can successfully segment out of Sentinel-1 SAR imagery. So we put that limit, and then the other limit is we flip the image. Basically, we are inverting the image. So especially when we're looking at melange, right on the top here, we see that when the detection will happen, it will take the entire region as an iceberg, which will be a big misclassification when we're looking at that, because that size icebergs don't exist for Greenland. So when we are inverting the image, the darker iceberg pixels convert to a brighter iceberg pixels. And that, on top of that, we implement the size threshold of 1,000 to 2 square kilometers, 1,000 square meters to 2 square kilometers. And when this is done, it helps us extracting icebergs from these complex regions, especially on the, as you can see on the right side of the image, we have the icebergs delineated out from the melange regions on the top. It also helps with the artifacts. For example, on the bottom right, you can see the artifact that is represented. It's no longer there in the final segmented image. So here, through dynamic thresholding, which is implemented on top of machine learning model, I'm able to create a binary image at 10 meters spatial resolution that identifies all the icebergs. And this is for one fjord that I'm showing right now. This is done for all 260 fjords around the Greenland Ice Sheet. Here are some of the results that we get. So on the left, you have the Sentinel-1 SAR imagery, and on the right is a final segmentation result that we get. And as you can see, there's a lot of noise in the Sentinel-1 SAR imagery. And I must say, this is one of the good scenes. So you can see that icebergs are clearly delineated. Then, and when the transition happens, this image setup becomes more and more complex. Here is another image. On the top left is the central one SAR imagery, and on the bottom right are the segmented icebergs that we see. And this is a snapshot within the Sermlik Fjord. On the left, you have the central one SAR, and on the right, we have the segmented icebergs. So to do a validation for this approach, we had a test data set. In total, we classified roughly 4 million pixels into icebergs and the background pixels. To determine the accuracy, because this is an imbalanced data set, we are looking at more pixels of background versus more pixels of iceberg. So we used an F1 score, and in total we got the F1 score of 0.72 for this particular study, and 0 represents the background pixels here, and 1 is the pixel representation of the icebergs over here. So here is the result of for the entire Greenland Ice Sheet. This is a snapshot for 2021. So on the left, the frequency size distribution histogram that you see represent one single mosaic of the entire Greenland Ice Sheet. So overall, we see roughly about 1 to 2.2 million icebergs in a single snapshot of 15 days. And on the right, you can see this is an image that represents all iceberg distribution for the year of 2015, for the year of 2021, every 15 days. So every 15 days, we are taking that snapshot and we are detecting the icebergs, and we are plotting that along with the total area that these icebergs represent. To see some interesting patterns that we find around the Greenland Ice Sheet, we saw that we divided the Greenland Ice Sheet into 7 basins. So the north, northeast, central east, southeast, southwest, central west, and northwest basins. So on the right is a heat map that I created that represents the total iceberg distribution in these basins and how it is changing from 2017 to 2021. And as you can see, there's a sharp decline or a drop that we see in March of 2018. And as we move forward, this drop persists till the end of 2021. In the northern basin, however, we don't see this drop, and one of the reasons is primarily due to the extensive sea ice cover that we have, and that resulted in the drop happening much later in early 2020. When we look at the percentage cover, so each fjord can be, you can look at icebergs as a percentage cover within each fjords of around the Greenland Ice Sheet. So we are looking at how much percentage of the fjord is covered by icebergs. So when I did that analysis, again, that drop around March of 2018 is seen across all the grid cells, all the 20 grid cells, except the north ones. So at one grid cell 1, you can see it goes all the way up to roughly 2020. So there is a large drop in percentage cover as well that is persistent in most of the grid cells around the Greenland Ice Sheet in this 5-year data set. So in conclusion, we created the first ever comprehensive iceberg distribution data set that covers all Greenland fjords for a time period of 5 years, every 15 days. So this resulted in finding some interesting patterns, especially the big drop that we saw in March of 2018. And these drop patterns are mimicked across from individual grid basins as well as at the basin level as well. And these shifts that we have observed are primarily due to were due to the sea ice winds and the wave patterns, because they are the only things that can change the iceberg distribution so rapidly around the Greenland Ice Sheet. And that shows that the environmental conditions around Greenland has a much higher impact on the iceberg distribution than the glacier velocities. Thank you. So the question is there any advantage, or did I see any advantage in any polarization that I'm using in the Sentinel-1 SAR imagery? Is that right? Okay. So I'm using both the HH and HV polarization just to increase the diversity in the data set, because we are already lacking in the number of bands that we're looking at, primarily because it's a SAR image. So what I did was I also, both the bands have their own advantages, especially when we are looking at HH polarization. It improves the contrast, and when we're looking at HV polarization, it reduces the noise in a lot of images as well. However, if we cannot use just one over the other. We're using both of them along with the combination that I created, which is the dot product of the HH and HV polarization band. Oh, so the question is that what is the ground truth data that I use when I show the confusion matrix? Let's move back. Yeah. So the ground truth was me and a colleague of mine. We labeled icebergs, and that labeling was the ground truth that we used to determine the confusion matrix. So the question is, what different data sets and repositories am I using? So in terms of the data set, I'm using the Sentinel-1 SAR data set. You can get it from directly from European Space Agency or Alaska Satellite Facility. You can get it from Earth Engine as well, because they house the data pre-processed, and that's what I initially had mentioned, that it helped take off 6 months of my work because they are already pre-processed. So I use the Google Earth Engine data catalog for this particular research. The question is, what happened in March of 2018? Was there a lot of heat events? So based on my research, I found that there was a sudden stratospheric warming event that occurred in March, around Feb to March of 2018, and that was the largest SSW event occurring since 1980. So that resulted in weather pattern changes from Greenland all the way to Rome. So I think that's probably one of the reasons that we see that drop, because the wind patterns were affected during that time.